Good morning. I'm actually going to do this in English because I need to talk fairly fast. I don't think you would keep up with all the little words that are different in Swedish and Norwegian. If my English sounds a bit weird, it's because I learned it from Canadians and Australians in combination. Don't try that. Anyway, I'm Rickard Westberg. I work in our Stockholm office at Knowit Defense Technology. We're a bit fewer people than you. We're about 17. So we're a small company, mainly catering to the Swedish defense material organization and helping them with designing the system before procurement. Anyway, I'm going to talk today about how you get paranoid and what you actually do about it when it comes to open source. So this is kind of a combination of all the things that you wanted in this seminar, except front-end, because front-end is kind of sorcery for me, so I'll skip that. Paranoia. It's not paranoia if they're actually out to get you. I claim that is actually untrue, because the paranoia comes from acting out of fear from something that you don't really know enough about. So all your measures that you use will at best be unproductive and at worst be directly counterproductive. Could you actually get someone to dress up like this? I've done experiments. You can at least get them to partially dress like this. I'm going to go back in time here. This is 25 years ago in Gothenburg, the Swedish Minesweeper HMS Gåsten. I commanded this ship for a year. It was one of the best years of my life. It was really, really fun. Yes, it's a wooden boat, and it's a fishing boat, but it has a story of itself. So, if you start spreading a rumor that during some of the exercises we encounter electrical and magnetic fields that may be harmful to the reproductive health, and then you just stock up on aluminum foil and see what happens. That's enough for that experiment, and I can tell you it succeeded. They sounded very, very strange when they walked around. So just inciting a bit of fear and making sure there are measures around makes people start using those measures, even though they are efficient or not. Of course, it was perfectly unharmful. As a side note, I flew SAS like 10 years ago and stumbled across an article in a magazine there, and I found my old ship in a fjord in Norway, painted differently. So if you want to experience my ship, you can actually go on a chartered tour with her. So there's my connection to Norway right now. My ship is doing fjord adventure cruises up here. While my boat went on to going for this kind of luxury environment, I went on to studying computer science at KTH in Stockholm. I focused on autonomy and machine learning 20 years ago, which was kind of a dead field. So I ended up at the Swedish defense company Saab. And having worked on ships, I, of course, continued working on ships, and specifically I worked on command and control systems in the weapon control area. So I may have a bit of a different background technically than most of you do, but trust me, it's still software and hardware, and all the bits that can go wrong are pretty much the same. So the ship in the background here is HMS Visby, the stealth corvette. And I've done a lot of coding, and I've managed a lot of projects around the actual software going into that, specifically with respect to the autonomous self-defense against the incoming missiles and so on. Over all the years working with this, I started realizing that, well, technology is moving ahead, and I can't keep working with all that old technology base, because you need to actually start looking at how do you make something smaller and more efficient that you can produce faster. So I started working with autonomous chips, and that's one of the platforms in the foreground, actually not mine. But it's a good picture, so why not use it here? That's when you realize that the tools that we used to use, they weren't really that good for what we were trying to get at. So things that we used to do, because we had a lot of cash, we had a lot of time, and we had a lot of people. We used to write our own operating systems. Yeah, it turns out when computers were new, you had to do that. And then gradually we went into actually employing commercial off-the-shelf operating systems with some pain. We did manual code reviews. We did manual testing. Manual code reviews out of binders with paper. That's really fun if you're a masochist. We did, of course, do waterfall models. And in a waterfall, you have that code and fix phase. So we were constantly in the spiraling water, never getting out of it. We had 1-year release cycles, and we had something called code freeze. How economically viable is a code freeze when you have 250 developers? Well, there's a lot of downtime, if you can use that. And as time started to move, we wanted to move faster. We wanted to use all the new buzzwords in CI, CD, DevOps, and so on. We wanted to go agile. We tried it in a few teams with success, but it never scaled on the larger scope. We wanted a higher degree of reuse. We wanted to go into the software-defined everything area, and not because we wanted to go there because it could do something we couldn't do right now, but because we realized that every piece of hardware will, in a few years, be software-defined. You can change its behavior with software. Software that you no longer get as a firmware from the supplier, but you can actually exchange it for something that you have open source. Software-defined networks, of course, being one of the most interesting areas in this case. And that's why I have the old classic, the network is the computer ad from Sun there, because it's becoming reality. In the cloud, in the compute engines today, the network is the computer, because that's the only way to keep up with Moore's law today. If you can see the move fast and break things motto here from Facebook, you should know that they changed it in 2014 to move fast with stable infra. So don't break things, because it will only hurt you. We wanted to use open source software, and I'll get into the economics of why we wanted to do that. But first, I'm going to take you through this. So what we had was a situation where we had our understanding for how computer architectures work that were based in the same year as the Atari 800 came out. And as you can see, it will never become obsolete. Actually, that text is stock full of marketing material that you can use for any computer system since the birth of time until up until today. It's the same thing we sold computer systems with every day, and none of them has ever reached the point of not becoming obsolete. The other example here is the Saturn V rocket, which exemplifies the models that we use, the methods and processes that we use to produce systems and software today, which actually has their base in the Gemini and Apollo programs at NASA. They developed the waterfall flow. And all the standards that we use today are derivatives of work done in the 50s, 60s, and 70s. And then you look at the internet and you find this. Change has never happened this fast before, and it will never be this slow again. And we were finding ourselves building a system where once we deployed the system, you could no longer buy the computer it was supposed to run on, and you had to start over. And we thought, yeah, this will pass. And then suddenly we realized, no, it won't pass. And the revelation here is that we felt like we were really, really good. And we were. The stuff we produced, it is actually world class. But there's a fictional self-help book for that. We didn't realize how much faster you could run if you could just do it in another way. And actually, this is a real problem that an organization faces today. When the technology starts moving really fast in an exponential way, which it always has done, it's just that we're at this part of the hockey stick right now. And an organization that is built to handle one problem can only learn logarithmically, which means that the gap becomes greater and greater. And you've heard a lot about this, I'm sure. You need strategies to actually jump up to the higher curve and keep up with that. That is not based in doing everything the same way you always did, but just a little bit better and differently. So what we came up with is a goal of replacing 98% of our in-system software with something that we did not produce ourselves. Of course, you can cheat on this. Just import the Chromium browser and you're done. but still. The reason for this is that you can stand on the shoulder of giants. You don't have to build everything yourselves. You get a lot of functionality that you didn't even know that you should specify. You share risk. You increase transparency of what you're actually doing. You can do it faster. And the main point that I found is that you increase learning. Because once you start looking at the problem of trying to understand your problem and finding something that can solve it, you stop focusing on your specific idea about how to solve all the small pieces. You have to generalize your problem, look for a component that fixes whole or part of it, and then integrate it together. And that's a whole different kind of learning process, and it becomes a combinatorial innovation process, which is really interesting. And I say that 98% in a really complex system, that is completely achievable. At Knowit Defense Technology, today we're doing an internal AI project for recognizing sounds recorded underwater. Yeah, it's aimed at a certain customer. We've written 500 lines of code. 250 lines of those are bash scripts. The rest of the code in the system is nearly 60 million lines of code that is just open source pulled in and used at the API level. Completely achievable. So when you try to introduce this in a high trust scenario, you get a lot of critics that say that no, you can't use open source because all of these reasons, it could be infiltrated. You have no process for it. You didn't specify the requirements before you built the open source, and so on. It's not reviewed. And what they all want is complete control. And of course, you can't have complete control when you're dealing with computers and software and so on, because I claim no one today has the mental capability to understanding everything that your system can do. The manual, the technical manual for the latest Intel processor is over 70,000 pages. All of them fairly relevant to how the processor works. I bet there's maybe that number of people who read it all. But it affects how your software executes. So you need to understand abstractions, and then you need to let go of the will to control everything. So, how can you trust software? I have a paranoid hint here. Your compiler is also software. We tend to focus on the customer solution, the delivered system in the end, and we put antivirus on top of that, and we have a secure operations team looking at logs, and we have audits and everything. But you should actually start looking at how you build trust at the beginning of the chain. Because if you haven't deployed it securely, you don't have a clue what is actually delivered and installed. If your product isn't safe, there's no point of deploying it. If your development environment isn't controlled, you don't know what's in your product. And if your supply chain, which from the beginning was a hardware perspective, and still kind of is, but it's coming into the software area. If you don't know what software you use in both your development environment and your finalized product, you have no clue what is actually in there. So, a supply chain concept for software. We looked a lot at this problem. And we realized that, yeah, you can review open source software. But if you buy software, like buying software from Microsoft, the Windows operating system, you get a contract with them. But you don't have really a clue what is actually in the software. So you call that secure by contract, because they have handled some of the security issues. And if you're in open source, you have to handle them yourself, unless you go into a contract with Red Hat and they handle the upgrades and so on. It's still open source. So to be agile in this process, you require automation, because if we look at Linux, during 2017 alone, it gained 2.5 million lines of code. That's a lot to put in binders and do manual code review on. Don't. It's actually worse than that. It was 3.9 million new lines of code, and the reduced 1.4 million, so that's why the sum total of gain is 2.5, but it's actually nearly 4 million lines of code that you need to put in binders. You need to automate this in some way. So what we looked at is, can we automate the capabilities that we want? Because if we can get it automatic and reproducible, we can also get it auditable. So once it's automated, you can start focusing on what are we actually doing in the automated machine, and is that good enough? And as soon as you have applied the automated machine, you get a receipt. We've done this. We've gotten this result. Instead of trusting 10 developers reading paper binders. And they're saying that, yeah, I've looked at everything. Yeah. So we started working down the list, and we started from the bottom. How do we actually get the open source? And ended up in understanding that we need something called secure download. Because if you download software from the internet, and you're a company that does high trust products, like Saab was, you're not guaranteed to get the same software at each download. We could download the same binary twice and get different checksums from it with 2 minutes apart. So you need to actually count. If someone is out to get you and you're a high-profile actor, they will go to those kind of measures. Next thing was actually bill of material. What is in my product? And I talked to someone yesterday saying that if you haven't looked at your full stack and you think that, yeah, I have like 5 things in there, your list is probably between 3,000 and 9,000 things, artifacts, versions of software that is actually in your product. Because stuff has dependencies that it pulls in. And you need to actually understand the implications of that. When we come to open source, you need to look at license evaluation. And actually, there are a few tools really good at doing this supply chain thing today, and all of them started as license evaluation tools. Have anyone heard about Black Duck? No one. Oh, you have. False positives is a word we use sometimes, but it's a really good tool. CVE scan, which is where security comes into play. Are there any known security vulnerabilities in anything that you use in your system today? And this is why we need the bill of material, not because we want to sit there and look at the 9,000 things that we have, but because if we don't know what we have, we don't know what vulnerabilities we have. So just make that automated, and you can just look up the CVE, which is a critical vulnerability enumeration. You find these online today, and they specify a cyber threat and the criticality of it. Tools for code analysis, benchmarking of your software, API checks. And API checks is actually a tool that you can use in your DevOps. Because if there's a new upgrade of the Linux kernel, the API check tool chain will tell you what will break if you pull that into your product. And not just the Linux kernel. Any software that you pull in, it will check that with respect to everything else that you use. There are great tools out there today. Don't pull it in and see what breaks. Know what breaks beforehand, because you can. The important thing here, if you want high trust, is to make it immutable and reproducible. And it will make it high assurance in the end. So, looking ahead then, we also looked at some next generation capabilities. And there are actually good tools out there today in production at a few companies. Facebook is using AI to patch code on a daily basis. What they do is that they have a machine that, once you feed it an error, it looks at how do you usually fix this, tests a lot of those bug fixes, and just repairs the code. Microsoft is looking at something called Sage, which they've been using for more or less 10 years, which is one of the main contributing reasons that Windows is very stable today. You don't get the blue screen of death that you got like twice a day before. I have an Apple on my computer, so, but still. They've become much more stable because they have rooted out errors that they didn't find before, just through code analysis in a completely different way. In Sweden, we have 2 French professors at the KTH University that are working on a tool that can fix code the same way that Facebook does, but with a lot more heuristic understanding of how code actually works. And just a while ago, there was a news announcement that their code actually committed fixes to real GitHub libraries under a fake pseudonym, getting the owner of the repository to think that it was a human that submitted that fix, commented that this is really good, and just pull it into its product. So today we have software that can actually fix software, which makes all of us obsolete, except the front-enders, because that's sorcery. So once you start doing that, you can have tools for optimization, which is really good if you go high scale. If you can scale down 15% of your compute budget, that's a lot of cash for those of you doing cloud. Diversification, which is something that a company called Maersk would have benefited from, because they had a monoculture in their computer environment, and they got a virus in their Ukrainian subsidiary, which took the company down in 17 minutes, laterally, globally. So if they had diversified their software, this wouldn't have happened. You can also, once you have a tool that is really good at looking at open source, you can get recommendations out of it. Because the tool chain you have knows what pieces of open source are good and which are not. So you should actually ask the tool, I need the best web proxy server there is out there today. And it will tell you which one that is from a trust and security perspective. Another piece here is certification. And DARPA in US is actually really interesting right now. They've done a project called Hackams. where they had an autonomous helicopter that were under attack from cyber attackers. They actually let the cyber attackers get a foothold on the flight control computer in the flying helicopter with the specific aim of take this helicopter down. And they couldn't do it because the software running the flight control software, the flight control mechanisms, were formally proved to be correct and without flaws, which means the hackers didn't have any way into that software. And the really interesting thing here is that it's not the software itself that is certified, it is the tool that formally checks the software that is certified. So if you apply that tool to your software and you pass, your software is passed. Instead of doing all the labor of getting certification on your application, you use a certified tool. We're not there yet for all software, but this is something that is going to be more and more common, specifically when it comes to systems that are in high trust applications. So the future is bright for those of you who want to use open source software and still be able to trust it. And that kind of concludes the thing I have. I usually end with that, because how could there be questions? And I think I have about, maybe a minute or two. So anything? Okay. Thank you very much. Thank you.